The small four-stroke engine has been the backbone of Briggs Stratton for more than 110 years. During this time, Briggs Stratton has seen many evolutionary changes that resulted in more power and a reduction in emissions. One thing that has remained the same for all this time: the use of four strokes to allow the engine to run. Engine design and configurations. This discussion of four-stroke theory will be based on overhead valve engines. These engines have valves that are installed directly above the piston and are built into the cylinder head. This is the most efficient design that lets the engine operate and maintain longevity. First, we will discuss the two types of engines Briggs makes: single-cylinder and V-twins. Then we will identify the differences between them, vertical and horizontal. Single-cylinder engines use one cylinder that supplies power. This design is sufficient for applications where moderate horsepower or torque is required. These engines range from 5.5 pounds per feet of torque to 21 horsepower. V-twin engines use two cylinders that supplies power. This design is suited for larger applications where more horsepower and torque is required. The range of V-twin engine output can range from 16 horsepower to 40 horsepower, which doubles the amount of work that can be done. Briggs Stratton offers two engine types beyond the number of cylinders. The vertical shaft engine is the most common engine. When the engine is mounted to its application, the crankshaft is in a vertical position. Vertical shaft engines are usually on walk-behind lawnmowers, pressure washers, lawn tractors, and zero-turn mowers. The second type is called the horizontal shaft engine. When the engine is mounted to its application, the crankshaft is in a horizontal position. Horizontal shaft engines are usually on pressure washers, lawn tractors, zero-turn mowers, log splitters, and construction equipment. Operation fundamentals. 3 conditions are necessary to make an engine operate. The first condition is a sufficient air and fuel supply. You can group this into one element. The second condition is an ignition source. A spark occurs at the spark plug gap. The third condition is compression. In order to have a sufficient energy released when the fuel and air is ignited, the mixture must be compressed. Without these 3 necessary conditions, the engine will not operate. Four-stroke theory. In a four-stroke engine, 2 full revolutions of the crankshaft are necessary to complete the 4 strokes. Four-stroke sequence is as follows: intake, compression, power, exhaust. The camshaft is a crucial component used to make 2 of the 4 strokes occur at the correct time. The camshaft is paired to the crankshaft with a gear set so that it correctly maintains the timing of the intake and exhaust valve events. The teardrop-shaped lobes on the camshaft also control how far the valves open and the amount of time they remain open. The camshaft turns at half the speed of the engine. For example, as the crankshaft completes a full revolution, the camshaft has completed 1/2 revolution, or 180 degrees. The camshaft will complete 1 full revolution when the crankshaft has completed the necessary 2 full revolutions to make all 4 strokes. The main role of the camshaft is to open and close the intake and exhaust valves. The flywheel on a 4-stroke engine is used as a source of rotational energy. The inertia keeps the engine turning. This is important because the engine only makes power to turn the crankshaft during one of the strokes. The flywheel makes sure that the engine continues to turn with sufficient speed to smoothly complete the 3 remaining strokes. The flywheel contains a magnet that makes electricity through induction. The ignition armature will cause a spark at the spark plug. The flywheel must be timed correctly to the crankshaft with a flywheel key. The ignition source for the power stroke will then occur at the correct time for accurate engine operation. Intake. When the engine turns and increases rotational speed, the piston moves inside the cylinder bore as the engine goes into the intake stroke. The camshaft opens the intake valve. During the intake stroke, the piston quickly falls inside the cylinder bore. This fast movement causes low pressure, or a vacuum, in the cylinder. The low pressure signals higher pressure outside the engine to equalize it. The outside higher pressure air moves through the air filter and carburetor. The fast airflow through the carburetor venturi gives another pressure change. The change in pressure lets fuel be pulled from the bowl to the carburetor directly into the incoming airflow. This air and fuel mixture will move into the combustion chamber before the piston is at the bottom of the cylinder. The camshaft will also close the intake valve. Keep in mind that some fuel can adhere to the intake runner. This wall wetting can cause inconsistent fuel delivery. This is common with carburetors and is compensated for. The intake stroke has been completed. Compression. With the two valves closed, the piston moves up to compress the mixture. As the mixture compresses, it makes heat, and the liquid drops of fuel turn into vapor, which will burn easily. The mixture is compressed approximately 8.5 times its original size by the time the piston is at the top of the cylinder. This compression process makes a more explosive mixture. When ignited, it gives sufficient force to push the piston down and turn the crankshaft. The compression stroke has been completed. Power. As the piston nears the top of its travel during the compression stroke, with the two valves remaining closed, the mixture is at its optimum point for ignition. Immediately before the piston is at the top of its travel, the magnet on the flywheel moves past the ignition armature. This magnet makes a small amount of electricity, which is amplified in the ignition armature to approximately 12,000 volts. This voltage moves instantly through the spark plug wire to the spark plug. The movement of electricity across the open air gap of the spark plug to the ground strap causes a single spark that ignites the mixture. As the mixture burns, it moves across the top of the piston. This causes a pressure wave, which pushes the piston and connecting rod, and turns the crankshaft with force. The pressure wave will act on the piston for most of its travel toward the bottom of the cylinder. The power stroke has been completed. Exhaust. When the piston is at the bottom of its travel, the camshaft opens the exhaust valve. The piston will begin to travel back up the cylinder, pushing out all of the remaining spent gases. This is important because these gases will not support combustion again and need to be fully removed from the cylinder. When the piston is at the top of its stroke, the camshaft opens the intake valve and the exhaust valve. This design feature is called valve overlap. Overlap uses the exhaust gases leaving the exhaust system to create a vacuum in the combustion chamber to help initiate the intake stroke ahead of the piston starting to travel back down the cylinder. This feature is part of the camshaft design and has no physical adjustment. The exhaust stroke has been completed. From this point forward, the engine will continue to operate and complete thousands of four-stroke cycles until the engine stops after you remove the ignition source or the fuel source.